Section 1.3 is called Reasoning and Logic, and the first thing we're going to start with in this section is what a statement is. A statement is simply a sentence that is either true or false. So an example of a statement would be, I ate cereal for breakfast. A non-statement or a non-example of a statement would be, what did I eat for breakfast? So this is a language issue, right? Is this what we talk about when you're in elementary school and you start to define the sentences that we create and how they are formed? So this is an example of something. What's the second one? It's not a statement. It's a question. There's one other kind of sentence that we form. Do you guys remember what it is? Did you get that, Nicole? The other one's a command. So when I tell my children, get to the car, it's not a statement. That is a command. Yes. It's not a true-false issue. It's not a question either. It shouldn't be a question. It should be a command. So that's another way that you can create something that is a non-statement. A negation is taking whatever the statement is and it's making it logically the opposite. Now sometimes that's easy to do and sometimes it's not quite so easy to do. Now the example I gave above with the I ate cereal for breakfast, it's easy to do the negation. We just say I didn't eat cereal for breakfast. We just use the word not in the middle of there. It doesn't always work out quite that easily. We'll see some later on here where it's not going to be so nice, okay? But for now, that's the idea that we were looking at when we make a negation. It's got a notation. You see that little tilde written in front of the P? That is the notation for the negation of or the opposite of P. All right, so very quickly we're going to run into some problems. And the problems we're going to run into are these things called quantifiers. Now, initially they don't look like problems, so let's just talk about what they are. Universal quantifiers are quantifiers that refer to every element in a set. The phrases that you see used or the word you see used when you have universal quantifiers is the words all, every, no, none. They're those words that get you into trouble when you use them with your parents, right? You always do such and such. You never allow me to go to that place. And your parents say, really? Always? Never? Okay. So those are called universal quantifiers. My example there was all people are sinners. Existential quantifiers simply refer to one or more elements in a set. So you see the phrases, there exists, or some. So my example is, some cats go to heaven. Okay, so you see that word some. Inherent in the phrase, some cats go to heaven, does not necessarily mean some cats don't. It just means we don't know about those other cats. Do you guys see the difference? So the problem with universal and existential quantifiers is that they make things really tricky when you're trying to do negations. So let me consider with you the first one, that all people are sinners. All people are sinners. What would be the logical opposite of that statement? Does it have to be no people are sinners?
Maybe some people are sinners.
Some people are sinners? Well, see, the whole idea is that we have to make it the opposite, okay? So Audrey's right in the idea of taking it and sort of making it into something about people not being sinners. But Taylor's also right in taking something and changing it from this idea of all people doing something to some of them not doing something. And think about with me what happens. And this happens, it's probably happened in every single one of your homes. You've said something to your parents like, you always make me go to bed at 9 o'clock. I know, that doesn't even make sense in terms of the number, but let's just pretend. You always make me go to bed at 9 o'clock. And your mom says, really? What about last Friday when you were out and you were out until 11? All it takes to make your statement not work is one time when mom did not make you go to bed at 9 o'clock. Right? That's usually what happens, right, is that you get some sort of feedback from that other person when you use those universal quantifiers and they say, really? What about this time? So when I take my statement about all people are sinners, all it takes to make that statement false is one person who is not a sinner. That's all it takes to make that statement false. And that would be the negation. There's at least one person, or we could say some people aren't sinners. All it takes is one. So that's what we're going to do on the next statement. We're going to do an all dog go to heaven one. Okay, so this is along the same ideas of my one where I said all people are sinners. So here's the idea. Anytime you see a universal quantifier, you've got to turn it into an existential quantifier. So if I see the word all, that is a universal quantifier. It applies to everything that comes after it in the sentence. I've got to change it to from a universal quantifier to an existential one. So I need to change the word all into what option? What are my options? Some, or there exists, or at least one, something like that. I like the word some because it's the easiest one to write because it only requires 4 letters. I like that one. It's quick. Some. Okay, so the existential or the universal turned into an existential. And then I have to take the next part and I have to reverse it. This says the dogs go to heaven. What's the opposite of that? They don't go to heaven. So some dogs don't go to heaven. Right? I don't need all of them to not go to heaven to make the statement false. I really just need one to make the statement false. But I can use the word some, and the word some will include the idea of being just one, and that's okay. All right, the second one says, some of my classes this semester are hard. So we're going to take the word some, which is which kind of quantifier? What is that? That is existential. It's telling you that something exists. And I need to turn it into the other one, which is called a universal quantifier. So what would you like to use as a universal quantifier in this case? All? All will work. Depending on the language that's surrounding will usually tell you which one makes sense. Like I could use the word every. That would be okay. Every one of my classes. I could do something with that too. All works fine. So all of my classes, what? What would I have to do to actually make this statement reversed, negated? All of my classes are what? Be careful. Is it always hard and easy? Yeah, we need to be careful. All of my classes are not hard. The reason we need to be careful is because sometimes there's that sort of gray area between, right? Just because something's not hard doesn't mean it's easy. It could just mean it's manageable and you don't really think of it being a big problem. But to me, when something's easy, it means I don't have to work at all to do it. And I can have to work a little bit and not call it hard. Are you guys with me on that? You just have to be really careful because your definitions are not mutually exclusive. When you say hard and you say easy, there is something that's besides that, something in between. Okay? So we're going to say are not hard. All of my classes are not hard. That would be the opposite of saying some of them are hard. All of them aren't. All right. Another idea in this section is that we're going to talk about truth tables. So truth tables are used to show all possible true-false patterns for a statement. So we're going to talk about a negation first. So if I have a statement called P, we already talked about the negation being called tilde P. So if the first statement is true, then the negation of the statement should be false. And if the first statement is false, then the negation of the statement should be true. And we can look back at our example that we just did over here to talk about one of these. Let's look at part B, actually, because this is talking about our class schedules. So this one says, some of my classes are hard, all of my classes are not hard. If the first one's true, the second one can't be, right? And if the first one's false, the second one can't be. They're opposites of each other. That's what it means to be negation. They're logically opposite of each other. Oops. Okay. The other thing we're going to talk about is how to combine statements together. So compound statements, or they're combined statements, are two statements joined with a connective. There are lots of connectives. The ones that we're going to see used the most frequently are going to be the words and, or, and if then. Okay? So some of my classes are easy, and I really like the school I'm at. Some of my classes are easy, or I really like the school I'm at. Those are different statements. If some of my classes are easy, then I really like the school I'm at. That has a different meaning, doesn't it? Okay, so there's 3 different meanings to those statements that we're going to look at next. Okay, so the first one's a conjunction. A conjunction is that and statement. And a conjunction is true only if both of the individual statements to start with were true. So, we're going to create a truth table. We've got one statement P, we've got one statement Q, and we're going to have the P and the Q combined. The combination or the notation for the conjunction is an upside down V. Now, the first thing I want to fill in is I just want to fill in columns P and Q. If you've seen truth tables before, you know where I'm headed. If you haven't, then I'm going to explain a lot, so hopefully you'll catch on, okay? Those of you who've seen this before, just use this as a refresher reminder how this works. One possibility is that both of the statements are true, right? A second possibility is that the first statement's true and the second statement is false. A third possibility is that the third statement's false and the second statement's true. And the final possibility is that they're both false. We are only going to work with 2 statements in this class. In contemporary, we often work with at least 3, or get to the point where we work with 3. You're only going to see 2 for what we're doing, okay? All right, so I'm going to use some examples of statements so that we can talk about this and sort of make sense of why in the world the result is what the result is. So I'm going to use the statement P, the statement being, I am a mom. And I'm going to use the statement Q to be the statement, I teach math. Okay, those are the 2 statements I'm going to use. And I'm going to try to combine these 2 statements, and as I combine these 2 statements with the word and, I'm going to give you an example in each category so we can make the decision of whether this works. So the first category has to be a statement where each of the statements are true, and that would be me. I am a mom and I teach math. So if I come into the classroom and I tell you, you see me standing here, I'm a mom and I teach math, you know that that compound statement is true because both of the individual statements were true. I'm trying to think of someone you guys know. Okay, so somebody give me the name of a female on campus that most of you guys know over in education who has kids. Don't use Dr. Aiken. You can't use her as an example here. Dr. who? Dr. Crane has kids. I wasn't sure if she did or not. Okay, Dr. Crane. Dr. Crane's an example of the second one. If Dr. Crane walked in and she said, I'm a mom and I teach math, the statement would not be true, right? She is a mom, but she doesn't teach math. She teaches special education. And there may be some components of mathematics in there, I understand that, but that's not what we're talking about when we say I teach math, right? So if she were to walk in and she were to say that statement to you, I'm a mom and I teach math, you would say, no, that doesn't work. That is a false statement when you combine them together with the word and. All right, so some of you have had contemporary math last semester, and you had it with Dr. Auk, right? Dr. Auk walks in. Dr. Auk is Tanner Auk, okay, for those of you who don't know. Dr. Auk walks in, and he says, I'm a mom and I teach math. And you would say, no, you're not, because he's a guy, right? He's not a mom. He actually is a dad, but he's not a mom, so this would be a false statement as well, yeah? Not going to work. Last example, Dr. Ferris. Dr. Ferris walks in, and bless his heart, he says, I'm a mom and I teach math. And you say, no. Lots of reasons why, right? Neither of those statements were true statements to start with, so certainly putting them together is not going to be true. So this is a false statement. So the reality is that when we're working with conjunctions, anytime the first two statements are true, the result's going to be true. And anytime either of the individual statements is false, the result is false. Okay? We're going to do the same thing now for a disjunction. A disjunction is an or statement. And we're going to use all those same people that we just had fun talking through. The notation actually looks like a V between the two individual statements. Now, the column setup for P and Q looks exactly the same. I still have all the same possibilities. I could have two true statements. The first one true, the second one false. The first one false, the second one true, or both false. And those are always going to be the same possibilities. Now, the results may be different. So let's go through these people again. If I come into class and I say, I'm a mom or I teach math, what would you say? Yeah, it's true. That is a true statement. I am a mom and I teach math, so I certainly have an or statement that would be working. Okay. All right. Who did we say? Dr. Crane, right? Dr. Crane walks in and she says, I am a mom or I teach math. And you would say, that's true. One of those statements is true, so I can put the or between them. That's a true statement. Dr. Auk walks in and says, I'm a mom or I teach math.
True.
It's true, yes. And for those of you, again, who don't know him, he does teach math. He is in our department. So, yes, he taught contemporary math. Last one, Dr. Ferris walks in and he says, I'm a mom or I teach math. Still false, right? Because neither of those individual statements are true. So when we're looking at an or statement, what does it take for an or statement to be true? Well, you actually answered the other question. Let me ask it the way that you answered it. What does it take for an or statement to be false? They have to both be false, right? The only time you get a false result in an or statement is if both of the individual statements were false to begin with. Any other time you get a true statement because at least one of the two statements was true. All right, so we're going to work on a truth table now. We're not working on context with these because we've already established how the truth tables work. So what we're taking a look at here is you're taking a look at, you've got a P, you've got a tilde Q, and you've got this combination with this conjunction. It's an and conjunction. So as I'm taking a look at this, what I want you to recognize first is you always are going to have a column for P and a column for Q. Always, always, always. I don't care what the statement has. If it has a P and a Q in there in some form, you're going to have a column for P, a column for Q. After that, you're going to look at the individual pieces and say, do I need any other individual statements? And you do. Do you remember what you need here, for those of you who've seen this before? I need a tilde Q, because my column actually that I will be using is the tilde Q column when I combine these. And then the last thing that I'm going to need is I'm going to need the P and tilde Q column. Now, the beauty in truth tables is this. They always start out the same. So you can always start them. Even if you get flustered and frustrated and forget what's next, you can start them. They're true, 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 false, false, true, false, false. Or sometimes I still tell students you can remember them as you go down. The P column is always two trues, two falses, and then the Q column oscillates. True, false, true, false. All right, so negation of Q. So I'm going to fill in the negation of Q column right here based on the Q column right before it. And how is that going to help me? What am I going to do?
It's the opposite.
It's the opposite. So if Q is true, then tilde Q is false. If Q is false, then tilde Q is true. And then I get that false true again for the same reason. Please make sure that your F's look like F's and your T's look like T's. I don't want to have to guess which one's which. All right. The last statement, which is really the point of this particular table, is to compare these two columns together, right? And it's to compare it using the connective and, right? This symbol right here in between there is an and symbol. When is an and statement true? When they're both true. So on the first row, I have true and false. What's that give me? That's false. On the second row, I have true and true. That's true. The third row, I have false and false. It's false. The last row, I have false and true. That's false. And that's our truth table for this.
So did you say you always needed the third one?
The tilde Q?
Yeah.
You don't always need tilde Q. We needed it in this one because the value that was starting with up here had a tilde Q in it.
Okay.
That's the only reason we used it. Yeah. Like for instance, you don't see us do a tilde P on this one. We could have a tilde P in a problem, but we didn't have it in this particular problem, so it doesn't need to show up in this particular truth table. Good question. All right, 3 is different. 3 does not tell you that you have to create a truth table, correct? Instead, it asks you to find what? The truth value. Now, a truth value is going to be found by creating a one-line truth table. So let me show you what I mean. We've got a tilde P, we've got a tilde Q, right? We're going to start out with P, Q, and then Brenna, this is where this one's coming in. I've actually got a tilde P and a tilde Q in this particular problem, so I need a column for tilde P and a column for tilde Q. And then my last column is going to combine them all into a what kind of statement on this one? It's an or statement. Now, an actual truth table where I put in all of the values here would be overkill. And it would be overkill because they actually give me some information that I can and should use. They tell me that P is false and Q is true. So I don't need any of the other combination possibilities. I know that P is false and Q is true. So that's the only line of the truth table that I need to consider. P is false, Q is true. Is this making sense? Don't do more work than you need to. Don't create a truth table when you only need one line of it. So if P is if P is false, what's tilde P? Good. And if Q is true, what's tilde P? False. And then we're going to compare these last two columns to create the or statement. So if I've got a true and a false, and I join them with the word or, what do I get?
True.
That is true. Now, this is the work that justifies what's going on. This is not your answer, however. Your answer is the answer to the question, what is the truth value? And that answer is this final value, whatever it is right here. It's true. That's the answer to the question. What is the truth value? It's true. And the work to support it is that one-line truth table that we just did. And you have to have both of them on your work to get full credit. Okay? Any questions on example 3? All right. We're going to take a look then at the next slide. It talks about statements being logically equivalent. Statements are logically equivalent if they have the same truth value in every possible situation. And you see it written, it's awfully small, I know, but what's between the P and the Q? It's not actually an equal sign. Can you tell what it is? There's 3 bars there. Okay? So logically equivalent is a 3-bar equality. And below you see what are called De Morgan's laws. De Morgan was a mathematician. De Morgan's laws actually are an example of logically equivalent statements. The value on the left is logically equivalent to the value on the right. In other words, if you were to create a truth table for this piece on the left, and you were to create a truth table for this piece on the right, the very last column of the truth tables of each of their two truth tables would match. They are logically equivalent to each other. Okay? Now, taking a look at that, thinking about that, let's take a look at De Morgan's law specifically. What does it look like happens? Let's just use the first one as an example. What do you see? What's it look like?
It looks like
It's a tilde,
it's distributed
Right, it looks like the tilde is distributed. So initially the tilde was on the outside, and now you see the tilde on each of the individual statements, right? What else do you see happened? It flips the and into a or, right? So the connective in the middle also reverses. It changes to the other connective. So instead of having an and statement, you now have an or statement. And the second one of De Morgan's laws is the same thing. It just means that it's just showing that if you had an or statement to start with, it would become an and statement. Okay, is everybody good with what you're seeing happen there? So the logical equivalent when you're using De Morgan's laws is to change each individual statement into its negation and to change the in-between connective to the other connective, and to or to and. And we're going to do one in symbols first. The first one we're going to do here, example 4 says, use De Morgan's laws to write the negation of P and tilde Q. So I'm wanting to write the negation of P and tilde Q. So this is what I'm supposed to be using. What does this become? Tilde P. Or, what would you say next? Q. So the first statement P becomes its negation tilde P. The and becomes an or, and the tilde Q becomes its negation, and the negation of tilde Q is simply Q. Does that make sense? Now, that sort of just looks like we're doing some fun stuff with symbols. What's the real value in that? I mean, what is really happening? Well, take a look. We're going to do an example in example 6. In fact, we'll skip 5 for a second and go to 6 so I can show you a concrete way that this works. It is not sunny and I will go for a walk. If I were to write the negation of that, I can use De Morgan's laws to do that. Because it would be really awkward to say, it is not true that it is sunny and I will go for a walk. They would look at you and they would say, I don't follow what you just said. It sounded like doublespeak, didn't it? It sounded like you had too many knots in there and I don't know what you are and you are not doing. So if I want the negation of that, what I do is I identify the two individual statements and the connective. And I can take each of those statements and negate them. So what is the opposite of it is not sunny? It is sunny. What do I have to do with the and? Change it to an or. And what is the negation of I will go for a walk? I will not go for a walk, or I won't go for a walk. And this second statement here is, in fact, the negation of the first. The first one says, it is not sunny, and I will go for a walk. That's what would happen if you went outside today, right, and walked across campus. It isn't sunny, and you're still going for a walk. The second statement then says, it is sunny, or I will not go for a walk. And that is the negation, the logical opposite of the first statement. Now I want to show you in example 5 here that they are in fact logically equivalent. So we're doing this from example 4. So in example 4 we found out that the logical equivalent to tilde P and tilde Q, like this, was tilde P or Q, right? So what I want to do is I want to create the truth table for this. And you know what, we'll just do 2 truth tables so we can think about it separately since they are done separately. The first truth table, well, both truth tables will have P and Q in them. The first one that was given here, typed in right up here, has a tilde Q in it. And then, again, this is like order of operations. You work inside of parentheses first. So we're going to put the part in parentheses first. We have P and tilde Q. And then we have the negation of P and tilde Q. And we're going to compare this to the truth table we get when we do the other one, which was PQ, tilde P. Okay, so I'm doing the one that we just created back here in example 4 over here. And then to join the tilde P with an or statement to Q. Are we all good? Each of those are different statements. What's that? You're slightly lost. Well, this.
P, Q, and the first one just. Can you explain it to me?
All right, so I got the part that's circled in red from the previous slide. We did this on example 4. We found that negation. What this problem is wanting me to do is it's wanting me to create a truth table for each one of them and to compare the final column when I'm done. So the part that's circled or squared in black, I created all the columns that I need for a truth table for the black one, working from the inside out. And then the one that's circled in red, I created all the columns that I needed for that one and wrote all the columns out. Now the columns start out the same way. They all start out true, true, false, false, true, false, true, false. So somebody tell me what the negation of Q column should say. False, true, false, true. I need to combine the P column and the tilde Q column. When is an and with the word and? When is an and statement true? When they're both true. So in the first line I have true, false, which gives me false. The second line is true, true, which gives me true. The third line is false, false, which gives me false. And the fourth line is false, true, which gives me false. And then the last column takes what I just did in this column right here and does what to it? It negates it. We don't have to do any not anythings. It just negates that column. So false becomes true and true becomes false. And then the last two falses also become true. So I simply look at the yellow highlighted column and I negate it. Let me finish this up real quick before we head out. Again, true, true, false, false. True, false, true, false. Tilde P reverses the P column, so it becomes false, false, true, true. And then we are going to compare column tilde P and column Q with the connective or. When are or statements true? When either one of them are true, right? So true, false gives me true. False, false gives me false. True, true gives me true. False, true gives me true. And I want you to compare before you head out those two columns at the end. They're exactly the same. True, false, true, true. So they are logically equivalent. We did the problem correctly. They did match at the end.